Hello everyone and welcome to this new video where we discuss mathematics and physics on the board. In this short video, what we are going to do is basically look at a simple example of a proof of what is called the Virial theorem. And this theorem is basically used in many situations in planetary physics, astrophysics in general, and also basically in quantum mechanics. And so we are going to see some applications a bit later on how we can use it for some kind of very nice heuristics. Okay, so let's consider the kind of problem we want to look at. So in this simple version, what we want to look at is one particle, and this particle is in a so-called central potential. So what that means is that the force that is exerted on the particle, one goes into a radial direction. Okay, so that's one aspect of it. So there is some sort of origin, the particle is kind of moving around, and the force that is being exerted on it is basically directed along the radial kind of, along a ray, if you will, that joins the origin to the particle. On top of that, a central potential implies that the magnitude of the force depends on the distance only and not necessarily on the angle, for example, in terms of the position of the particle. Okay, so in fact here let's denote the central potential V of R, and here the position of the particle is R with an arrow on top, so it's a vector, it has a direction and magnitude, but the magnitude then I'm going to denote it R here. R is equal to the magnitude of R. Okay, now the velocity, I'm going to denote this R dot, and so this is dr over dt, that's the instantaneous velocity, and then the momentum is simply m times r dot. So that's a traditional kind of notation. Now we call virial, so that's an actual quantity, the quantity that I'm going to call here vir, and that's equal, that's a definition, to p dot r. Sorry, not p, that's f dot r. Apologies. So that's the dot product between the force exerted on the particle and then dot the scalar product with the position vector itself. Okay? So what we are going to do actually is start from the virial. Okay? And so I'm going to look at the virial. So I've got that f dot r. So I'm starting from that line and I'm writing that the virial is equal to f dot r. And now what I'm going to do here is basically apply the principle that the force I'm looking at, by definition of a central potential, it means by the word potential that it is a conservative force. And so what that means for me is that this is going to be equal to minus, and then because it's a central potential, is going to be dv dr. So that's for the force in the radial direction, that's the unit vector in the radial direction, and then dot r. Now it turns out that that r here can be written as a magnitude times this unit vector. So what I can do here is tell you that this unit vector r I've defined here is by definition equal to the actual position vector itself divided by the magnitude of it. So that's r divided by its length, if you will. Okay, again, that's simply a property of central potential or forces that are centrally kind of directed, or like sometimes people say spherically symmetric. So here I can use that property, and basically I'm simply going to get that this is minus. In fact, V, the potential only depends on R. And then here I'm going to get simply R here. So that's a simple kind of quantity, this virial. But what is interesting, that's one aspect here, but then I can also write something else. But also, we have that the same virial is equal still to F dot R, but then I'm going to use, assuming I'm somewhere in an inertial frame, but also provided inertial frame. And if you don't know what I mean by that, I will put a link to one of the videos that I made where I actually discuss what that means to be an inertial frame and why this is essential when doing any form of mechanics. Basically, what I can do here is apply Newton's second law. And so write that this is equal to dp dt and then dot r. Okay, so one of the things I can do here is basically perform the kind of manipulation you would do when performing an integration by parts. So I'm going to recognize that dp over dt dot r can also be written as the derivative of p dot r. Okay, so momentum dot r, and then minus the other derivative that would come from the product rule. So that would be minus p and then dot dr dt. Okay, so essentially that would be something like this. You've got d of p dot r dt, so that's one thing, and then you're going to get minus, so let's write for now, so r dot, and then if I use the, depending on what you want to do, you can write either p here and convert it in terms of the velocity, or express here the velocity in terms of the momentum. It's really up to you. Let's actually do, as far as I'm concerned, expressing the velocity in terms of the momentum. So I'm going to have d of p dot r dt, and then we are going to get minus p squared over m. And here, actually, what we recognize is that this quantity is twice the kinetic energy. So this quantity here is equal to twice, and let's denote the kinetic energy Ke here, just for simplicity. Sometimes people call it T, some other times just K. Let's call it here Ke for kinetic energy. Okay? So what we are going to get is the following. If I actually put these results together, we actually get, therefore, that minus dv dr r is equal to dp d of p dot r and then dt minus basically 2 times the kinetic energy. Okay? So then what people do usually is that they are going to put, whichever they want on whichever side. So, yeah, so for example, I can put let's actually keep it like this for now. Okay, so let's keep it like this for now. And what people then do is they introduce the time average. So you introduce a notion of time average. And the way you do that is you simply say that the average of a function, that is a function of time, over a period t is going to be equal by definition to 1 over t, and then the integral, let's say from 0 to t of f of t dt. So that's the definition here. So what people do then is they say, well, let's have a look at what happens if we take the infinite time average of this equation. Okay, so basically you're going to have minus, and in fact, yeah, let's continue with the minus. So minus, and then you've got dv dr r, okay, and then that's equal to, and that's here I'm going to say this is the infinite time average, and here you're going to get d p dot r and then dt. So that's again an infinite time average, and then minus twice the infinite time average of the kinetic energy. Okay? Now, what we are going to do here is basically calculate this thing, because this is a time derivative, and this is a time average that involves an integral, which is an antiderivative with respect to time. So, as it turns out, this quantity is going to be, because we take t to be infinite, this thing is going to be, it can be written at least as a limit when tau tends to, when big T, I'm going to write a big T because that's what I wrote earlier, big T tends to infinity of basically P dot R evaluated at T minus P dot R kind of at time equals 0. And the whole thing is divided by the period T. Okay? What happens is that you can look at some classes of motion. And one of the things is that if your motion or the orbits or trajectories of the system you look at are so-called bound, then what you're going to obtain is basically that these quantities have like maximum values to explore. Okay, so if trajectory are bound, okay, the numerator here has to be finite in magnitude. And because it's finite in magnitude and you divide it by something that goes to infinity, then this whole quantity is going to go to 0. So if trajectories are bound, then these quantities here is going to be, then it is finite. And consequently, you're going to get that the totality of this is equal to basically 0. Okay, this average. And so this leads, in fact, to the Virial Theorem. So I'm going simply to erase quickly on that side, and we can then move on to the next step. Okay, so let's formulate then the Virial Theorem here in a simplified case. So Virial Theorem is basically telling us that dv dr r is equal to, well, in expectation value, infinity is equal to 2 times the expectation value of the kinetic energy. Okay? Now, usually this is presented in a different format, but that's not related to the general theorem. So to actually find a typical format this is kind of offered, we need to actually look at a model. So a typical model. And the typical model in question is basically if you choose V of R to be equal to some constant divided by R. Okay, so that would be the case for the electrostatic interaction between 2 points, 2-point charges, or the gravitational force between 2 masses as well. Okay, so in that case, if you look at, you've got dVr dv over dr is equal to minus c over r squared, and then multiplied and then multiplied by r, you get that dv dr times r basically becomes minus c over r, which is actually minus v of r itself in that case. So when you've got a power law, then essentially you get a kind of more meaningful kind of case where the potential energy, so you're going to have the expectation value of the potential energy is going to be equal to, or the time average is minus twice the time average of the kinetic energy. Okay, and that's something that is incredibly useful when we actually look at, as I said before, as we look at orbital mechanics, but also when we look at some, at least, ways of dealing with, let's say, macroscopic physics, including atomic physics and molecular physics. So that, again, these are some things we are going to look at a bit later. Okay, so if you've got any questions or comments about this, by all means, do let me know, and otherwise, see you in the next video.